All right, so let's continue with convergence test for series. Right? So our next theorem will be a theorem on convergence test. Right? So suppose we have a Q series sigma of xn and sigma of the yn. Right? And suppose we have two positive series, right? Right. Suppose that the first series is smaller than the second series. The terms of the first series is less than or equal to the terms of the second series. Right? So if the second series converge, then the first series converge. So you can think about this. You can think that the first series is a small series and the second series is a large series. If the last series is finite, then the small series is also finite. Right? And similarly, if the first series diverge, then the second series diverges. So if the small series is infinite, then the last series has to be infinite as well. Right? So using this, we can test many other series whether other series are converged or diverge as well. So, for example, if we take a sum of n squared plus 1, right? So in this case, we can use integral test or we can use a comparison test, right? So you see that 1 over n squared plus 1 is less than 1 over n squared, right? So you can see that the series, if I write sigma just alone, then it's not a good notation. It should be sigma and with the indices as well. So this, so you can compare our first series with the p series with p equals to 2. And the p series, when p equals to 2, the series converge. And our original series is smaller than a series which converge, right? So we see that our original series converge. All right, so this is the first example by the comparison test. So we have two comparison tests. So let us call our first theorem the comparison test number 1. Right? And we'll have another comparison test, which is comparison test number 2. So we have, as before, two positive series. Right? And we suppose that if we take the individual terms and we divide them, right? And then we take the limit as n goes to infinity. Suppose this limit is this, right? Then we conclude that the two series has the same convergence. If one series converge, then the other series converge. If one series diverge, then the other series diverge. Right. So this is our second comparison test. Right. So we have two positive series. We have the quotient. The quotient has the quotient xn over yn has a limit. Then the series either converge or diverge. Right. So so as before, right? But now we have the series 1 over n squared minus 1, right? Before we have plus, now we have minus. If we use the first comparison test, right? Then 1 over n squared minus 1 is greater than 1 over n squared, right? We have the series, the sum of 1 over n squared converge, right? But using the first comparison test, we cannot conclude that the sum of 1 over n squared minus 1 converge. We cannot conclude that, right? Because the small series converge doesn't imply that the large series converge, right? So we have to use the comparison test number 2, right? The second one, right? So we also compare with the series the sum of 1 over n squared, but instead of using a bigger than or smaller than, we use the quotient, right? So we have to use the comparison test number 2. So we compare the series 1 over n squared minus 1 with the series 1 over n squared, right? We take the individual terms, 1 over n squared minus 1, divided by 1 over n squared, right? So this is equal to n squared over n squared minus 1, right? But now we take the limit. As n goes to infinity. We see that this limit is 1, right? Bigger than 0, right? So we conclude that the two series has the same convergence or divergence. However, we know that the p series 1 over the sum of 1 over n squared converge. Now by comparison test number 2, we can conclude that the original series converge. All right, so any questions? All right, so we have many tests for convergence or divergence. So let's move on. So all right, so our next theorem is a theorem of D'Alembert. It's also a convergence test, right? So suppose we have a positive series, and then we take the quotient x n plus 1 over xn, right? We take the limit as n goes to infinity, and we suppose that this limit is this. So let us call this limit L, right? So we will we consider three cases, right? So the first case is if L is less than 1, right? The second case is if L is greater than 1, right? And the third case is if L is equal to 1. So in the first case, then the series converge. In the second case, the series diverge. So these theorems can be proved, and you can read the proof in the lecture notes. I don't have enough time to cover the proof, so I'll let you read the proof in the lecture notes by yourself. So in the third case, uh, we cannot say anything, right? So we cannot say anything about the convergence or divergence of this series, right? All right, so this is the theorem of D'Alembert, right? So so let us do a small example, right? So let's consider the series n over 2 to the n, right? So if we use the theorem of D'Alembert, right? So here x to the n, x sub n equals n to the 2, n over 2 to the n. Right? So we form x sub n plus 1 over x sub n, right? So it's n plus 1 over 2 to the n plus 1, right? Over n to the 2 to the n, right? So now you can see that this is what? This is n sub 1, n plus 1 over n, right? Times 1/2, right? 2 to the n over 2 to n plus 1, right? But we see that this is 1/2, right? And the first term, n plus 1 over n, goes to 1, right? As n goes to infinity, right? So so we see that the limit of x sub n plus 1 over x sub n is 1/2, is less than 1, right? So by D'Alembert theorems, we conclude that by D'Alembert, we conclude that this series converge, right? So we have a series, the sum of n over 2 sub 2 to the n, right? And then we use the D'Alembert theorem to show that the quotient has the limit 1/2, less than 1, and we conclude that the series converge, right? So any question? So our next convergence test is a theorem of Cauchy, right? So the D'Alembert theorem and the Cauchy theorem has the same hypothesis, right? So the first hypothesis are the same. So suppose suppose this is a positive series, right? And the second hypothesis is different, right? And suppose that we take instead of taking xn plus 1 over xn as in D'Alembert, we take another expression. We will take xn and we take the nth root, right? Right. Suppose this limit is this, right? And then we also consider three cases, right? If L is less than 1, right? If L is greater than 1, and the third case, if L is equal 1, right? The third case, if L equals 1, right? In the first case, the same as before, we say that the series converge. In the second case, the series diverge. And in the third case, we cannot say anything, right? We have to use another method. All right, so So with the Cauchy theorem, we can study the convergence of more complicated series, right? Say let us look at the series 2n plus 1 over 3n plus 1 and to the n. Right? This series is very complicated. Right? If we do not have Cauchy theorem, then we have a very hard time to evaluate this. Right? So this series, we can use the Cauchy theorem. Right? So we have x of n is n 2n plus 1 over 3n plus 1 to the n. Using Cauchy theorem, we take x sub n is greater than 0. We take the nth root, right? So taking the nth root is 2n plus 1 over 3n plus 1, right? When n goes to infinity, right, it's go to 2/3, right? And this limit is less than 1. So by Cauchy theorem, we conclude that the series converge. Right. So this is an example of how to use Cauchy theorem. Right? So we have quite a number of conversion tests. So all right. So next we have an integral test, comparison test, and so let us make a note here. So integral test, comparison test, two comparison tests, right? And D'Alembert theorem, and Cauchy theorem. These theorems applies for positive series, right? These apply for positive series, and remember this, right? If you want to apply the theorems correctly, then you have to remember that they apply for positive series. All right, so let's move on to another type of series called alternating series, right? So sometimes you see that we have a series like 1 plus say 1 plus 1/3, 1 3 square, 1 3 cube, 1 3 4, and so on. Right? Or we have 1 over 1 over 2, or 1 over 6 square, 4 square, and so on. So here we have all the terms are positive, so we have a positive series, right? But in many other cases, we don't have positive series. So for example, we have a series with arbitrary sign. For example, we have 1 plus 2 minus 3 plus 4 plus 5 minus 6 plus 7 plus 8 minus 9, and so on. So we can have 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on. Right? So we want to compute this series as well. We want to compute the series with size plus or minus size as well. Right? So let us make a definition of an alternating series, right? So all right. So an alternating series, say, is a series of the form minus 1 to the n times x of n, where x of n is greater than 0. So, for example, 1 minus 1 2 square plus 1 over 3 square minus 1 over 4 square plus 1 over 5 square, and so on. So this is an alternating series. This is an alternating series. However, if we have a series like 1 plus 1/2 minus 1/3 plus 1/4 plus 1/5 minus 1/6 and so on, this is not an alternating series. Because alternating means that the signs plus or minus have to be next to each other, right? So alternating series, what do we call it? In Vietnamese we call it chuỗi đàn dấu. And all right, so we have defined alternating series, right? And next, let us make a definition for absolute convergence and conditional convergence. Right. All right, so now we consider an arbitrary series, right? So we call it absolutely convergent. If so, this is a definition, right? If the series of absolute values converge, and we have a theorem which says that if the absolute series converge, then the normal series converge. And this theorem can be proved. You can read the proof in the lecture notes. Right? So using this theorem, so you see that by the theorem, right? So if a series is absolutely convergent, then both the absolute series converge and the normal series converge. Right. So if the absolute series converge, then the normal series converge. However, there's a case that the absolute series diverge, but the normal series converge, right? So uh, uh, let us make an example. Right? There's an example that we see later. That so uh, let us consider the series 1 minus the alternating series, which looks like a P series, right? But the signs are alternating. Right? So this series is actually alternating series. So we have to adjust the sign a little bit. Right? So this series uh, is absolutely convergent, because uh, if we take the absolute value, right, we have a P series which converge. Right? So this is our first example. So our next example, right? If we take the series 1 minus 1 half plus 1 third minus 1 fourth and so on. Right? So this is a series uh, minus 1 to the n plus 1, right, times 1 over n. Right? So in this series, in this case, if we take the absolute value, right, if we take the absolute value, then we have a P series with n equals 1. And in this case, we call this a harmonic series. We call this harmonic series. Chuỗi điều hòa. This harmonic series diverge. Right? However, the alternating harmonic series converge. However, we see later that this converge. Right? So the absolute series diverge, but the normal series converge. In this case, we call it conditional conversion. Right? In this case, we say that the alternating harmonic series. So we call this alternating harmonic series. Uh, is conditional conversion. Not absolutely convergent. Right. So let us make a definition. a series sum of xn is conditionally convergent. This is the definition, right? So when I use the green color, I often write a definition. If the absolute series, let us call this the absolute series, right? The absolute series converge, but the absolute series diverge. But the normal series, the original series converge. Right? So this is the definition of conditionally convergent and absolutely convergent. So in Vietnamese, conditionally convergent is bán hội tụ, and absolutely convergent is hội tụ tuyệt đối. Right? So you need to know both the terminologies in Vietnamese and in English. Right? All right, so let's there's a very interesting theorem which is called Leibniz criterion, right? So Leibniz. Let me check. So Leibniz criterion. So Leibniz criterion applies for alternating series, right? So we have a theorem which is called Leibniz criterion. Right? So suppose we have an alternating series. So in this case, we have x sub n is positive. If the sequence x sub n, right, is a decreasing sequence, and they go to 0, right? Then by Leibniz theorem, this alternating series, then the alternating series converge. So Leibniz criterion applies to an alternating series with individual terms go to zero, and the individual terms have to form a decreasing sequence, right? So now we can use the Leibniz theorem to study many interesting series like 1 minus 1 half plus 1/3 minus 1/4 and so on, right? So let us study this alternating harmonic series. So if you want to call it in Vietnamese, it's chủ ý điều hòa đang dấu. All right, so this is equal to the sum n goes to ends from 1 to infinity minus 1 to n plus 1, right, times 1 over n, right? So this is equal to right. So if we take x sub n equals 1 over n, right? So this is a decreasing sequence. Someone has question, right? Như các bạn có câu hỏi đúng không? Có bạn nào đang bật mic có đặt câu hỏi không? So this is a decreasing sequence which has limit equal to 0. Right? So by Leibniz theorem, right? So by Leibniz criterion, we see that the alternating harmonic series converge, right? But does it converge conditionally or absolutely? Or absolutely? Does anyone know?
Conditionally.
Right, that's correct. It only converges conditionally, right? But not absolutely. Because the absolute series is the harmonic series, but the harmonic series diverge, right? So in this case, it only converges conditionally. Very good. All right, so we are doing quite good. So let us. So previously we learned D'Alembert theorem, and also we learned remember the D'Alembert theorem for positive series, which takes the quotient and we consider the limit of the quotient, and also the Cauchy theorem for positive series, which we take the nth root, right? So now we have a generalized D'Alembert theorems and a generalized Cauchy theorem for arbitrary series, right? So let us move on to so generalized can be written with Z or with S, so it's up to you, right? If you like American English, you take Z. If you like British English, you take S, right? So I study in both. I study in both England and America. Right? However, when I write, I prefer British English. It's just a it's just a it's just a habit choice, right? So I use S. Right? So generalize D'Alembert theorem, right? Let us take the generalize D'Alembert theorem. Right? So all right. So suppose we have uh, a series, right? And it satisfies that the limit Sn goes to infinity, right, of xn plus 1 over xn, right? But now we don't take the normal quotient anymore. We take the absolute value, right? And suppose that this limit exists, right? So we can do as before. We consider three cases, right? One, if L is less than 1, right? Two, uh, if L is greater than 1, and 3, if L is equal to 1, right? So you remember previously, if L is less than 1, then what can we say? Anyone? Does anyone know? If L is less than 1, what can we say about the series? Does anyone remember?
Converse, absolutely.
Right, that's correct. Then the series converge absolutely. Very good. It doesn't only converge, but we can say more. We can say that it converges absolutely. Right? If L is greater than 1, then what can we say?
Diverse.
Right, we say that it diverges, right? But here we can only say that the absolute series diverge. Right? And in the case L is equal 1, right? Then we cannot say anything, right? It's it's uh, then it's inconclusive, right? We cannot say anything about this case, right? So it is a generalized theorem of generalized D'Alembert theorem, right? Now we have also a generalized Cauchy theorem. Uh, Maybe we can say Cauchy theorem or Cauchy criterion. Right? So let us change. All right, so let us change this theorem to criterion. All right. So as before, you can guess what this criterion say. generalized Cauchy criterion. So suppose we have a series such that you take the n terms and you take the nth root, right? But in this case, we don't know about the sign of the individual terms, so we take the absolute value, and then we take the limit as n goes to infinity, right? Such that this limit exists, right? So as before, we consider three cases, right? If L is less than 1, right? If L is greater than 1, and the third case, we have L is equal to 1. So what can we say about the first case? Anyone guess? Just as before, right? Using the D'Alembert theorem or using Cauchy theorem. Then the series converge absolutely. Not only converge, but we can say that it converge absolutely. Right? If L is greater than 1, then we cannot say that the series diverge, right? But we can only say the absolute series diverge. And in the third case, it's inconclusive. We cannot say anything. Right? All right, so this is the generalized Cauchy theorem. And in the absolutely convergence case, in the absolutely convergence case, we have a very interesting theorem of Dirichlet. Right? So about the rearrangement of series. Right? So what does it mean, right? So for example, we know that Euler says that 1 plus 1 over 2 square plus 1 over 3 square plus 1 over 4 square and so on. Right? We know that is equal to pi squared over 6. Very beautiful. Right? So how about if we take 1 plus 1 over 3 square plus 1 over 2 square, right? Like instead of adding like previously, we rearrange the terms. Plus 1 over 5 square plus 1 over 4 square, right? Plus 1 over 7 square plus 1 over 6 square, right? What is it equal to? Right? Can anyone know? So we rearrange the terms, right? So we ask what is it equal to? Right? How about this? We know that 1 minus 1 half plus 1/3 minus 1/4 plus 1/5. So this series converge by Leibniz, right? We did before is alternating harmonic series, right? Leibniz criterion, right? So how about if we take a 1 plus 1/3, let's say minus 1/2 plus 1/5. We rearrange the terms in many other different ways. Plus 1/6 minus 1 plus 1/7 minus 1/6 and so on. Right? So we ask whether it converges and whether these two series are the same numbers. Right? So we don't know. We don't know. Right? So there's a theorem of Dirichlet. This is called rearrangement. We are rearranging the terms of the series. Rearrangement of the series. So there's a theorem of Dirichlet which says that suppose we have an absolutely convergent series, right? So then any rearrangement of this series also converge absolutely, and it converges absolutely to the same value as the original series. Right? So you see that Dirichlet theorem is a very interesting theorem. It says that for our question, for our first question, right? Our first question, this is actually also equal to pi squared over 6, right? By Dirichlet theorem. So this is called the rearrangement of series, right? All right, so let us make a note for how to apply applying a convergence test. Right. So until now, we have many convergence tests, right? So for positive series, what do we have? We have integral test. We have a comparison test. Not only one, but two comparison tests. And we have what do we have? We have D'Alembert criterion. And we have Cauchy's criterion. Right? So that's for positive series. And for alternating series, we have a Leibniz criterion, right? For arbitrary series, we have generalized D'Alembert criterion. We have a generalized Cauchy's criterion. Right. So you see that for any series, so for an arbitrary series, you can use any of the above criterion, the above convergence test, or criteria, and sometimes you have to combine different convergence tests in order to check the convergence or divergence. So we will have many practice problems in the exercise. Right. So we'll do many practice problems in the exercise classes. Right? So any question?
Yes, I have a question.
Yes, please.
I have a series that 1 plus 1 over 2 plus 1 over 3. I mean, the P series with P is equal to 1 is a divergence series. But according to the D'Alembert theorem, we have un plus 1 over un is smaller than 1. So it must be convergence. Why this is contradict?
Thank you. This is a very good question. But you're asking about the harmonic series, right? So this is a very good question. If you use D'Alembert's criterion, then un plus 1 over un is you have to take the limit, right? The limit of that series is actually equal to 1.
Yes.
Right? So if the limit is equal to 1, then it's inconclusive. You cannot say anything, right? You have to apply another convergence test, right?
Yes.
So does that answer your question?
Yes.
All right. It's a very good question. Sometimes for a series, if you can solve a series by one test, you can try another test. That's very good. Any other question?
I have two questions.
Yes, please.
So the first one is that what is the motivation at first for the people to study the infinite series? I don't think that is only because it's beautiful.
Yes, okay.
And the second one is that can you name some application in some field of applications or some example of the infinite series, and especially if something that related to our major.
Okay. This is Q&A. All right, Q&A. Right. Questions and answers. Right. So. What is the application of series? Right. This is actually a very good, very good question. Excellent question, actually. Yeah. So I'll tell you the answer, right? My answer. There may be many other different answers. So one is as I am a mathematician. I am a mathematician, right? So I would say that people study it because it is beautiful mathematics. It's true, right? This is true. Like mathematicians study mathematics because it is beautiful. Right? So this is one answer. Right? So the second answer is later on you see that first a series, you remember the dictum, right? Is a number. Remember this. This is very important. Right? A series is a number. So you can represent a number as a series. So you can have things like before. You can think that it is interesting because you have identities like 0.9999, right? It is actually equal to 1. You can use series to prove this. But later on, you will learn that later on you study series of functions, right? And now a series of functions is a function. Later on you see that, right? A series is a number, but of a series of functions is a function. So later on I'll tell you about the series of functions. And later on, you see that this is very important. So I'll make a note. A function can often be represented by a series. So you know that there are many functions that we learn, like sine, cosine, or the exponential function, and these series representations allow us to compute functions, right? And not only their functions and their derivatives, not only their derivatives and that, but also their integrals, right? So this is a very important application of series. So when you study technical things like computer science or maybe engineering, you have many special functions, right? So you have many special functions, right? You have special functions like in calculus 2, you have a gamma function, right? And later on, when you study differential equations, you have a Bessel function, right? Bessel functions, right? And maybe zeta functions as well, right? Then these functions can be represented by a series, use series to understand this function. And without series, you cannot understand these functions well, right? So this is the application of series. Does that make you happy? Have I answered your questions?
Yeah, Kyle.
All right. Your questions are very good questions. Yeah. You can ask what are the applications of this series, and they are very. So I'll mention one. I'll mention before, and I'll mention again. Remember the dictum. The dictum. A series is a number. And later on, I'll tell you another dictum. A series of functions is a function. Right? And another dictum, a function can often be represented. Sorry, represented. Represented by a series of functions. So these are three dictums, very important, right? If you remember this dictum, you will know why you study these things and how these things are useful. Any other questions? All right, so if there's no question, let me turn off the recording now.